In this video, we're going to do some practice problems related to the related rates problems. So our first example, an oil tanker collided at midnight with an obstacle. Oil spills from that tanker so that it forms an ever-growing disk centered at the place of the accident. How fast the disk grows depends on several factors such as wind, temperature, currents, etc. At 10 a.m., the disk has measured 0.5 miles. The radius has measured 0.5 miles. And at the time the radius is growing at 0.01 miles per hour. How fast is the area of the disk growing at that moment? So we're going to do our step-by-step process. Step 1, we're going to draw a picture if possible and assign variables. All right, so what we're doing here is we have some kind of oil tanker, some kind of boat, and it has spilled oil in the ocean. And that oil is in the shape of a circle, a little more circular, and it's growing at a certain rate. So there are two things that we're looking here. First of all, we can see that we are asking how fast is the area of the disk growing. So our first variable is going to be area. We'll call that A. And note that we are trying to find the derivative dA dt. The other variable that we're considering is the radius. And note that the radius is growing at that time at 0.01 miles per hour. So we are given that dr dt is equal to 0.01 miles per hour. So here's our one variable where we're given the rate, the other one where we want to find the rate. And note that this is at the point when r is equal to 0.5 miles. So step 2, this is what's really going to change from problem to problem, other than the variables we're going to be looking for, is what equation do we have that can relate these two variables together. And in this case, we could use the area of a circle. That A is going to be equal to pi r squared. And remember that what we have here is that we actually have functions of t. Area is a function of t. R is a function of t. So when we take this derivative, we have to do implicit differentiation. So now let's do that implicit differentiation. We're going to take the derivative with respect to t of a and the derivative with respect to t of pi r squared. So the left-hand side is just dA dt. That's what the derivative of a means. That's what we're looking for in this problem. And the derivative of pi r squared is going to be pi times 2r. And then you have to use the chain rule, so we have to multiply by the derivative of r. So step 4, we have all our values. We've taken our derivative. Let's plug it in and answer the question. We're looking for dA dt, and this is going to be equal to 2 pi. R is, at this point, 0.5 miles, or just 0.5 miles, and the derivative at that point is 0.01 miles per hour. So this is our answer. We can simplify it if we want. Let's actually just leave it like this. This is going to be our unsimplified answer. The area is changing at that rate. It is growing, so it's a positive rate. There we go. That's going to be, I guess we can write it as 0.01 pi, which is 0.0314 or so. All right, let's do it a couple more times. Next problem, a baker rolls a 300 centimeters cubed thing of dough so that the shape changes radius and length, but not its total volume. So when you're rolling out dough, like you're baking something, you're not changing the volume of the dough, but you are changing the shape. The radius and the length are changing completely. So when the length of the cylinder is 12 centimeters, the length is growing at 0.1 centimeters per second. At what rate is the radius of the cylinder changing at that moment? So step one, we have some cylinder here of dough, and we have a few variables. So we are rolling this out. So as time is going on, this cylinder is becoming skinnier and skinnier. We want to track how fast is that length and radius changing. So let's look at the variables, what we have, what we're looking for. The question says, at what rate is the radius of the cylinder changing? So R, we're going to call the radius, and we want to find the derivative of R. We're also given a rate L. The length is growing at a certain rate. So L we'll call the length. And we are given that dl dt is 0.1 centimeters per second when L is equal to 12 centimeters. So before we go any further, let's actually try to guess what the answer will be. Not what the answer, but the sign of the answer. Here, the radius, or we can see by our picture, the length is getting bigger and bigger, but the radius will be getting smaller and smaller. So we should expect dr dt to be negative. We'll see if it actually works out. That might be a check to see if we're doing something right. All right, step two, we need some kind of equation that relates R and L together. In this case, we can use the volume of a cylinder. That is, V is going to be pi R squared times L. Sometimes we see that as pi R squared. H, in this case, we're just putting the cylinder on its side, so it's a length L. And note that V is constant in this problem, right? The volume does not change. So here we go. Step three, take the derivative. We have on the left, we have the derivative with respect to t of v. And on the right, we have the derivative with respect to t of pi r squared L. So it may be tempting to write dv dt on the left, but v is just a constant, and the derivative of a constant is just 0. It's not changing, so its derivative is 0. On the right, we have to use the product rule. to take care of that derivative. So we're going to do the derivative of the first, pi r squared, times the second, L, plus the first, pi r squared, times the derivative of the second, L. So this is going to give us 0 equals, the derivative of pi r squared is going to be 2 pi r times the derivative of r times L. We have to use the chain rule. R is a function of t. We have to take the derivative of the inside. On the right, we have pi r squared, and then the derivative of L, dl dt. And note that we are trying to find dr dt. So let's plug everything in. We know that L is equal to 12 centimeters. We also need to have R. We have dl dt is 0.1 centimeters per second. We need to find R real quick. So you need to find R when L is equal to 12. In this case, we're actually going to have to use the fact that we have 300 centimeters cubed of dough. This is V. V is constant. It's equal to 300. So if I want to find R, I can plug it into the equation that 300 is equal to pi r squared times L, which is 12. So we have R is going to be equal to, we have pi r squared is going to be 300 over 12. R squared is 300 over 12 pi. So R is going to be the square root of 300 over 12 pi, which we could write as the square root of 25 over pi, or 5 over square root of pi. All right, so now we have everything. Let's plug it in. 0 equals 2 pi. R is 5 over square root of pi. We're looking for dr dt. L is 12 plus pi 5 over square root of pi squared, and dl dt, which is 0.1 centimeters per second. So we could write that 2 pi 5 over square root of pi dr dt times 12 is equal to negative pi 5 over square root of pi squared times 0.1. So dr dt, what we're looking for is going to be negative pi over times 5 over square root of pi squared is going to be negative 25 times 0.1 all over, right, that is 2 pi 5 over root pi times 12, which we could write as maybe negative 2.5 over 120 square root of pi centimeters per second. Unsimplified, we could write it as we did before. It's fine. Note that we expected our answer to be negative, and our answer was negative, so that's good. It is decreasing. All right, next question. A rocket is launched from a platform straight into the air. A camera placed 500 feet away on the ground is tracking its progress. The angle between the line of sight of the camera and the rocket and the ground is changing at a rate of 5 degrees per second. What is the speed of the rocket when the angle is at 45 degrees? So let's draw a picture here. We have some rocket. It's being launched from some launch pad, and there is a camera that is tracking its progress 500 feet away. So the distance here is 500 feet. And we're going to be looking at this kind of picture. Let's label everything we have. What are we looking for? Well, it says, what is the speed of the rocket when the angle is at 45 degrees? What is the speed of the rocket? So we're going to let's call it x, is going to be the distance off the ground of the rocket. That's going to tell us the speed that it's changing. That is dx. We're trying to find the derivative of that distance. So that's our x. The other variable that we have here is the angle between the line of sight of the camera and the rocket and the ground is changing at a rate of 5 degrees per second. So we'll call this angle between the line of sight and the ground, we'll call that angle theta. Let's call it the angle at the moment. And we are given that d theta dt equals 5 degrees per second. So, step 2, we need an equation that relates theta and x together and hopefully incorporates that 500 somewhere as well. We may think Pythagorean theorem since we have a nice triangle here, but that is not really going to help us here. We really do need a trig equation. In this case, we could use tangent of theta is equal to x over 500. Whew. And we want to find the derivative of that with respect to t. So let's think about this derivative. We have d dt of tangent of theta on the left and ddt of x over 500, which we can also just write as 1 over 500x. That might make it a little bit easier. On the left, the derivative of tangent of something, we have to use the chain rule. This is going to be secant squared of the inside times the derivative of the inside, d theta dt. And on the right, this is just going to be 1 over 500, a constant, times the derivative of x. We're looking for dx dt, so I'm going to just solve for this right now. Usually we've been plugging it in before we solve, but we can do it the other way around. This is going to be 500 secant squared of theta secant squared of theta times d theta dt. All right, we know that theta is going to be 45 degrees, and we know that d theta dt is changing at 5 degrees per second. There's one thing that we do have to do, and that is we need to change this value to radians. It's not going to make sense to think about degrees per second. We really do need radians there in order to complete this correctly. So we need to translate that. That's a little difficulty in this problem. But if we want to change this into radians, we need to multiply by pi over 180. Which will be pi over 36 radians per second. We don't need to change the 45 degrees, even though we could, to pi over 4, because we're plugging it into the trig equation itself. So you have 500 secant squared of, we'll call it pi over 4, it's better to use that anyways, times pi over 36. Let's think about secant squared of pi over 4 real quick. That's going to be 1 over cosine squared of pi over 4. Cosine of pi over 4 is going to be 1 over square root of 2 over 2. In fact, it's better to write this as 1 over root 2 squared, which is 1 over 1/2, which is going to be 2. This all turns out to be 500 times 2 times pi over 36, or 100 over 36 pi. This is going to be feet per second. Or we could write this as 25/9 pi feet per second, fully simplified. So I want to make clear that this is a different kind of problem dealing with trig functions, same kind of related rates thing. This difficulty of degrees and radians is the least important part of the problem in terms of this section, but it's worth seeing in Calc 1 that degrees actually really screw things up in problems. If you use the 5 degrees per second instead of the pi over 36 radians per second, your answer would be dreadfully wrong by a huge amount. And you would get that the speed of your rocket is way, way faster than what it actually is. So it's good practice to just take everything in terms of radians. That is going to be an important thing to do in most problems. In review with all these related rates problems, each of the steps was pretty similar with a couple big exceptions. The equation that we used per problem was different in all the examples we did, and you're going to see different ones as well. The derivative of those equations is then different. But other than that, it's really not much different from problem to problem. I hope we can see the difference between these problems and the optimization problems. These deal with rates and finding a rate. Optimization deals with finding the minimum or the maximum of something. They're completely different problems, although they're kind of back-to-back sections and are word problems.